All right, thank you everybody for coming. So this will be the first lecture of the spring 2025 class, Introduction to Spacecraft Navigation, which is now, I think it's co-listed as main 4964 and main 6964. It really is a graduate level class, however you slice it. But folks enrolled in the 4964 will have it just a tiny bit easier. But yeah, looking forward to a great semester. I have kind of a canned spiel, which is mostly borrowed from last year's first lecture, but there are a few modifications. So I'm going to go ahead and share my screen. Hope this goes okay. All right. A quick thumbs up or some audio confirmation that you can see my screen and it's a PowerPoint with space and words like spacecraft navigation on it.
We can see it.
All right, much appreciated. Thank you. All right, so let me go ahead and if there are any issues or my audio cuts out or something, feel free to interrupt. So yeah, this is lecture one of Introduction to Spacecraft Navigation. Really glad that everybody could be here. I regret this having to be a fully remote class. I would have liked to have taught you in person, but you'll see as we go through the slides on my background why it's really not possible to do it that way. So we're kind of making the best of the situation. So really quickly about myself. So I grew up in New York State. Actually, I grew up in Rensselaer County, very close to RPI. So on the diagram on the right, Troy, New York is the little gray area with the gray arrow pointing to it. And then just about 20, 25 minutes away is the small town of Averill Park, which is the red area. And that's where I grew up. So RPI is almost my hometown. I really didn't go away for college. And I went to RPI for a long time. So I um, graduated Averill Park High School in 2013. So I'm 29 right now. I got an associate's degree at Hudson Valley Community College, which is just up the road from RPI. So I did 2 years there, getting my general education out of the way. Highly recommend community college to anybody that's thinking about. I mean, obviously not this crowd, but there are folks that look down on it. I think that's a mistake. I think some of my best years were at Hudson Valley. And then I transferred to RPI in 2015, and I got a BS in mechanical engineering, graduating in 2017. And then I stuck around. I did what used to be called the co-terminal program. I think it's changed its name, but that is the stick around for a year, get a master's degree program. And I did that. I got a master's of science in 2018, studying with Dr. Kurt Anderson on CubeSat attitude dynamics and control. And then I continued to stick around, which is um, a, a dubious idea. Not everybody should get a PhD, but I decided it was a good idea for me, and I stuck around and I signed on with Dr. John Christian, who now teaches at Georgia Tech. And I did my research on autonomous optical navigation, and I got my PhD in December of 2022. So all told, if you count the fact that when I was in high school, I actually took some RPI classes for credit, I was technically at RPI for a little over 10 years. So I've been there for a minute. And while I was at Hudson Valley, I was taking kind of cross-registered courses as well. So long history at RPI. While I was there, I spent a good chunk of that time pursuing my PhD and working as a teaching assistant. And in general, RPI likes you to be a TA a handful of times, not 7 times. That was kind of exceptional for me to be a TA 7 times. But I really, really loved being a TA. I was not expecting to, like, I kind of wanted to just do my research, get a PhD, and go home. But while I was at RPI, I absolutely fell in love with teaching and with just all of it, office hours and helping people. And RPI, as I'm sure you've noticed, it's a rather challenging school. It's easy to feel like you're getting beat up when you're an RPI student. And I absolutely fell in love with kind of shepherding students through classes that had beat me up when it was my turn, and trying to kind of soften the blow just a little bit, trying to make the office hours that much more helpful, or trying to just kind of be there to help out or just be an encouraging word. Um, and fell in love with it and decided that the first thing I wanted to do when I graduated was turn around and teach. So these are all the classes that I TA'd. I got an award for being the top TA in the main department in 2018, 2019. And I made up my mind that I wanted to turn around and teach. The thing is, I also wanted to work at NASA, and you can't really do both of those things unless you're a real weirdo like me, which I managed to work it out that I did both of those things. So I got my PhD in December of 2022. I'm pictured there in the top right with Dr. Kurt Anderson, who was there at my hooding ceremony, filling in for my PhD advisor. And I got a job working as an aerospace engineer in the Aeroscience and Flight Mechanics Division at NASA Johnson Space Center. So I'm pictured there on the bottom in the Space Shuttle simulator, or on the right, taking lessons on how to use a nautical sextant for navigation. So working at NASA now, I just drove home from work. So I'm kind of like, I work at NASA full time, and then I teach nights and weekends. So that being said, this is not a NASA course. This is not NASA approved. This is not, this does not get the NASA seal on the side of it. This is something that Paul is doing with his nights and weekends. So your mileage may vary. Um, and so, how did this class come together? So, wanted to highlight some of the folks that really made this all possible. So, of course, Dr. Kurt Anderson, top left, he was my master's advisor and was definitely a big part of my life all throughout getting a PhD. Now he's technically my boss, which is a lot of fun. And him and Dr. Maniati, I believe the head of the main department, were kind of early supporters of me teaching a class as a remote adjunct professor, which really doesn't exist. Like that's not a that's not a position that's listed, a remote adjunct, but they were able to kind of shoehorn me in, along with Dr. Tom Haley, who's just been tremendously helpful. I was emailing him just a few minutes before this class started, kind of getting things all squared away. Um, and so, yeah, people throughout the main department are big champions and supporters of me being able to teach remotely and try to kind of pass along what I've learned. Also, some folks on the NASA side. So Dr. Chris D'Souza on the bottom left, kind of one of my major mentors, infinitely more qualified than I am to teach this course, by the way. He's taught all of this content to astronauts before. Very, very phenomenal teacher, great mentor, great friend, just an all-around good person. But he is not available and I am, so you're stuck with me. But Chris is a great guy, and he kind of gave me a pat on the back and gave his verbal blessing to go and teach a class like this. But of course, NASA, if you work for NASA, you work for the federal government, and you can't just go have a second revenue stream without approval. So I could not, for example, moonlight as a professor or moonlight as anything without the express authorization of my division chief. So that's Carlos Festelli. He's my boss's boss. And actually, I got approval from Julie Kramer-White, who's the head of all of engineering at Johnson Space Center. She also is okay with this class happening. So a lot of strings had to be pulled to kind of get this NASA RPI connection. But probably the biggest thumbs up goes to Dr. John Christian, who's pictured there on the right. So he was my PhD advisor. He taught me almost everything I know about spacecraft navigation. Now he's a professor over at Georgia Tech. He's actually working on getting a textbook published, which I highly recommend that you check out as soon as that goes through publication. But he taught a version of this class. So he taught main 6962 spacecraft navigation in, I think that was spring of 2018. And I took that class, and I just kind of soaked up all I could learn from John, and then also from Kurt. And this class is me kind of regurgitating the best of what I have come to understand, and then also with a twist of like emphasizing the things that we actually use day to day at NASA. So definitely, this class would not exist without these folks, and I wanted to linger on that for a minute. So how is this class going to work? I've mentioned this already. I work full time at NASA. And so this is a nights and weekends commitment for me. So I can do lecture 3 to 4 hours a week, office hours 2 hours a week, and sometime on the weekends. But that's about it. I'm really not going to be as accessible as your other professors just because of the way my time is split, which means you're going to need to be a self-starter. And I really, really strongly recommend working in groups. I think it would be a bad idea if you tried to solo this class. You'll find that the assignments are pretty difficult. I would go as far as to call them brutally difficult. And you really want to treat this class as a series of group projects. You can work with different people throughout the semester. You can work with the same people. It's really up to you how you want to handle it. But please, for the love of Pete, don't try to solo this class. Go get with a group. And if you're struggling, or if you're of a more introverted persuasion, talk to me, and I'll see if I can't kind of sort out some groups as well. But yeah, this is meant to be a kind of a group project class, because the thing is, real engineering is a series of group projects. That's what you have to look forward to after you graduate. And like I said, I can only really promise to check my email once a day. So we'll do our best. But yeah, you're going to need to be pretty independent throughout this class. So ethical disclaimer, I've kind of touched on this before. Some of you, so most of you have my RPI email address, of course, but also my NASA email address, and some of you have my personal email address. And then some of you, I think, have my personal cell phone number, which just the nature of like I've been involved in RPI for a long time. I know some people more than I know some other people. But I want to make sure that I'm fair to everybody, and I don't want to give anybody any preferential treatment. So I want to make some policies. The first of those is anonymous grading. So please do not put your name on your homework assignments. Please put your RIN on your homework assignments. I will, so LMS has a feature where you can do grading completely anonymously. And then once you have your grade, then it will pop up and go, oh, so-and-so got this grade. And then also, if you're going to contact me about this class, contact me over email only. So if you text or if you have any other way of contacting me and you reach out, I'm going to slap you on the wrist and say, don't do that. I really want to try to be fair to everybody. So those are the rules. Email if you have a problem, preferably mckeep2@rpi.edu, and then only write your RIN on your homework assignment. And I'll remind you about that when the time comes to turning your homework. So now it's time to start talking about guidance, navigation, and control. And so kind of pivoting from the way the class is run to what is this class all about. Actually, we're going to start in the middle. We're going to start at the top. That makes the most sense. So navigation is determining a vehicle's state, so position, velocity, or attitude, as well as other parameters of interest. Okay. So navigation is where am I? Guidance is determination of a path or trajectory to take the vehicle from its current state to a desired future state. So guidance is where am I going? Guidance is I'm currently at this speed and altitude and I want to be at this speed and altitude. Let me find some curve that kind of takes me from point A to point B, right? Or I'm currently at this position, I want to be at this position. Find some path that gets me from point A to point B. That's guidance. And then control is actually making the guidance solution happen. So that is sending voltages to actuators, letting gas out of thrusters, and using these actuators to move a vehicle along the trajectory described by guidance while maintaining stability. So those of you that have taken something like modeling control of dynamic systems or any other controls courses, that is the control side of things. Guidance is really a variation on optimization. So if any of you have taken, for example, optimal control theory, or if any of you are familiar with like calculus of variations or using other fancy math tricks to kind of solve problems of finding an optimal path, maybe a fuel optimal or a time optimal path, that's guidance. And then navigation is an extension of estimation theory. Estimation and control are kind of two sides of not exactly two sides of the same coin, but they're very similar. They complement one each other well. Navigation, which we'll be focusing on in this class, is just where am I? So taking measurements of your surrounding and using those to deduce your position, velocity, and attitude. So that's what we'll be talking about this semester. So the course topics, we're going to begin just with some, very preliminary stuff over the course of the next couple of lectures. Then we're going to get into a review of orbital mechanics. So I believe spaceflight mechanics is a prerequisite for this course. If you haven't taken it or if you're rusty, we are going to go through a 2 or 3 lecture kind of crash course on orbital mechanics. So definitely make sure that you are locked in and paying attention for those lectures. After that, we're going to set the groundwork for the rest of the class with a discussion of estimation theory. And that's really going to be when we eat a pound of dirt, right? It's going to be the slow, we're going to be very rigorous with our mathematical framework and our foundation. And then the class gets to be more and more and more fun after that. So then we start to spend some time on space to Earth and Earth to space navigation. So like GPS or like Deep Space Network, inertial navigation. And then it gets even more fun. Star Trackers is probably my favorite unit. So by the end of the class, you will have written an algorithm to process a starfield image and then determine your attitude in space. Sequential state estimation, if you've heard of Kalman filtering, we'll talk about that. And then at the very end of the class, we'll talk about kind of the modern state-of-the-art image-based navigation technique. So taking images of the Earth, taking images of the moon, taking images of, for example, lunar terrain to try to determine where be the broad overview of this entire course. And here that all is expressed visually. So I'll let you kind of stare at this for a minute. This is a map that I've made where all of navigation is expressed somewhere on this map. And we're going to return back to this almost every lecture because I think it's important to kind of, I mean, if we're navigation engineers, we want to know where we are. We want to know what we're learning and what we're studying and how it relates back to the big picture. I think one of the biggest kind of mistakes that I see happening in some classes is, you know, the professor will say, okay, today is going to be lecture 19, and we're going to be talking about this. And it's like, right, but why do I care? I'd like to spend a little bit of time every lecture on, okay, why does today's lecture matter and how does it fit into everything else? So to start, let me kind of guide your eyes here. So you've got a spacecraft traveling from the Earth to the Moon on this kind of figure eight trajectory, something like Apollo 8 or Artemis 2. And so as the spacecraft is kind of moving along this dotted line, that represents orbital mechanics, which is going to be kind of the start of the class. Right. When you go back to the Earth, you see that the Earth is sitting on the back of a turtle, and underneath that is another turtle, and then it's just turtles all the way down. That is a joke. That's a Stephen Hawking joke. I believe he makes that in A Brief History of Time. He was talking to a flat earther, and he asked them, well, if the Earth, they believe that the Earth was on the back of a turtle. And he said, well, okay, what's the turtle floating on? And the person said, oh, it's just another turtle. It's turtles all the way down. So that's the joke. I hope that lands. If it doesn't, sorry. But if there were something that was at the base of all the turtles, it would be an abacus, which is kind of a visualization of mathematics. Math is kind of the foundation of everything else. So we'll move from orbital mechanics to estimation theory, which is going to be the foundation of everything else that we do. From there, we'll go to the pink lines, triangulation and trilateration. So that's how to determine where your spacecraft is from ground-based measurements, or if you have a spacecraft like a GPS satellite, how to determine your position on the Earth from spacecraft-based measurements. From there, we'll talk about inertial navigation. That is the 3-axis gyroscope that you see there in the bottom middle of the image, which is kind of a instrument that's on board the spacecraft that allows, it's a little bit like the way your inner ear functions. You can kind of feel acceleration and rotation, and the spacecraft can do the same thing. The next unit will be star trackers. That is the kind of light orange color of the 3 stars. So a lot of modern spacecraft have cameras that take images of stars and use those to determine their orientation in space. We have a whole unit on that. The bottom right, the little robot looking thing, that is my PowerPoint art visualization of the Apollo guidance computer. So we're going to talk about Kalman filtering, which is a sequential estimation technique that allows you to kind of continuously track and update your best guess of where your spacecraft is. And that is going to be a very interesting, very useful unit. Kalman filters are completely ubiquitous on modern spacecraft navigation algorithms. And then finally, we'll land on the kind of green image, which is taking pictures of the moon, or you could also take pictures of the Earth or of any other planet, but that's going to be image-based optical navigation. And so we'll spend a little bit of time, whenever we change topics in this class, we'll go back and go, okay, here's how what we're doing today relates back to the big picture. This is the big picture. So homework policy, there are going to be 7 graded homework assignments, and they are each worth 10% of the overall course grade. So every homework assignment is a letter grade. Do not skip the homework assignments. Homework will be due roughly every other Friday at close of business, submitted via LMS by 5 o'clock Eastern time. There is no guarantee that late work will be accepted. Now, last year when I taught this class, I didn't have any issue with people handing in things late. I don't see there being an issue this year. Please get your stuff in on time. If you have some extenuating circumstance, I am reasonable, like if something came up or I don't know, we can talk about it. But here's what you don't do, right? Don't just be late and then go, oh yeah, sorry, my car exploded and I can't, I'm sorry. It's like, let's try a little harder than that. If you have an issue, tell me as soon as there's an issue so that I know that your work is going to be late. And I'll be reasonable about that. But I do reserve the right to apply a grade penalty. If I think that you're not being reasonable with me, then I reserve the right not to be reasonable either. But I don't see it going that way. I think it's all going to be, I think everyone's going to be nice and chill this semester. That's what I'm hoping for. Like I mentioned before, anonymous grading, RIN only. Don't put your name on your homework assignments. And collaboration is fine. Collaboration is encouraged. But I would ask you to write the RIN of all of your collaborators. And each student is expected to write their own report. So basically, the entire class is going to be these 7 really brutally difficult homework assignments. Those of you that have taken spaceflight mechanics with Kurt Anderson, you might remember the pendulum problem, the Grand Canyon problem, and the realistic rocket problem. Each of these homeworks are at least that difficult, and there's 7 of them. So that's the hard part of the class. There's definitely going to be some challenge there. The good news, soon I have some good news. The term project is worth 20% of your course grade. The term project is basically another homework assignment. So it is as if there were an 8th homework assignment. And if you can't think of a topic for the term project, then I'll just give you an 8th homework assignment, basically. But the term project is worth 20% of the overall course grade. I'd like you to go out and do some research on your own. So go read a journal or a conference paper, and I will provide a list of those, or you can go off on your own and go find one. Please, let's go through, and I'll remind you about this, but when the time comes to really get started on the term project, let's talk one-on-one about what your topic is and make sure that we define reasonable goals, and kind of stretch goals and then fallback goals. But what I'd like you to do is read a paper, thoroughly digest it, be able to reproduce it somehow. So if you read a paper on some batch estimation technique, can you code it up yourself and then get the same results or similar results to what they have? Be able to explain the paper concisely. So this is really going to be one of your only opportunities in this class to practice your communication skills. And communication is absolutely critical for any engineer. And finally, I'm expecting a 20-minute presentation from every student. And this will be basically the very last day that I can ask you to do it, which is the Wednesday before study days, so right before the finals start. So that is the expectation on the term project. So if you're doing math, let's see, 70% of the class is homework assignments, 20% is this term project, which is basically another homework assignment. So 90% of the course grade is homework, 10% is participation, which if you just show up to class and are even reasonably engaged, I'm comfortable giving everybody 10%. So exams, if you've been doing the math, there isn't any percentage left over for exams. There will be no exams in this class, but there's an asterisk. Just kidding, there's no asterisk. We're not doing exams. I think exams are a poor idea, especially by the time you've made it to graduate school. You've proven that you are intelligent. You don't have to prove to me anything. I'll be able to tell whether you get the content based on your homework assignments. I don't need the exams. Also, as I think we saw during COVID, it's basically impossible to maintain academic integrity on an online exam. And I really just don't have the energy to go through and be the cheat police. I don't want to do that. I want this class to look as much like real engineering as possible. And like I said, real engineering is group projects. So that's what we're going to be focusing on. There's also an extra credit opportunity. So if those of you that have heard of the video game Kerbal Space program, you'll be thrilled to know that you can get bonus points in this class by playing that game. And those of you that haven't heard of it, I highly encourage you to go check it out. It's on Steam. It is a computer game where you play as these little frog-looking alien people, and you build little spaceships. You can build rockets, and you can take them to space. And it's this perfect blend of cartoony and realistic, where it's goofy, it's silly, but you really do kind of need to know how rockets work to put something in orbit. And there really is such a thing as orbit. There's a lot of space video games where it's like, okay, click this button and you'll go to space. And it's like, no, in this game, you actually kind of have to think about staging, and you have to think about like prograde or retrograde orbits. And I was playing this game as I was taking spaceflight mechanics for the first time, and it really helped me build an intuition for oh yeah, plane change maneuvers they take a lot of delta V. Like I kind of knew what that meant intuitively just from my time with Kerbal Space Program. Actually, a couple of semesters ago, I think it was Professor Singh was teaching an advanced spaceflight mechanics course. Maybe it was the undergraduate spaceflight mechanics course, but I was talking with one of his students, and apparently they did a poll in that class of how are you doing in this class right now, and do you play Kerbal Space Program? And the correlation was staggering. It was like people who had played Kerbal were the A and B students, and people that had never picked it up were the C and D students. And I would like all of you to be A and B students. So the way this is going to work is if you can demonstrate to me, either by a screenshot or a video or share screen, I mean, we'll figure it out. If you can demonstrate to me that something that you've built has got to orbit, and like, if you've already done this, then like do it again. Just take a screenshot really quick. Then you'll get 2% extra credit. And if you can do an Apollo-style moon or Mun landing, which is to say, one vehicle splits in half, part of it goes down to the surface, part of it stays in orbit, lunar orbit rendezvous, and then safe reentry back to Kerbin or to Earth. That's worth an additional 3%. So if you do all of that, that's worth 5% on the course grade. So that's not 5% on a homework assignment. That is half a letter grade in the entire course for this amount of work, which for some of you, this is half an hour in Kerbal Space Program. For others, this might be 10 hours. But either way, I think it's time well spent. And I just adore this cute little video game. So I highly recommend you check that out. So as I mentioned before, grading, the breakdown is going to be 10% class participation, 70% homework, 20% term project, and then up to an additional 5% Kerbal Space Program. I reserve the right to introduce other extra credit opportunities. So for example, last spring, you got an additional 5 points if you applied to be an astronaut, or if you demonstrated that you had completed the application. Whether or not you submit it is up to you. That I don't believe there will be an astronaut application cycle this spring, but who knows? If something comes up, then I might offer other extra credit. Here's my policy, and this is kind of my poorly kept secret. My intention right now is to give every single one of you an A. I don't want to give out any A minuses. I don't want to give out any B pluses or any other grades. I want to give everybody an A. If you are approaching something other than an A, if you're handing in B tier work or C tier work, I will tell you. I will reach out to you and let you know that something is going wrong. But otherwise, I want everybody to relax and not think about grades at all. Right? I just do your work. If something isn't going well, then that's between you and me, and we'll figure it out. But yeah, you're all grad students at this point, or you're very nearly a grad student. GPA is not on my radar. I don't think that's important. I think what matters is how much you know. So, I think somebody has a hot microphone right now. Yeah, like I was saying, my intention is to give everybody an A in this class. Now, if I will give out, intermediate grades, you'll get a grade on every assignment. If you do have a grade appeal that you would like to go through and talk about it, then I would like you to reach out to me within 1 week of receiving your graded assignment. But like I said, I'm not expecting a lot of the grade appeal. I think this is worth 2 points instead of 3 points. We're not playing that game. This is going to be, you're going to work really hard, and then you're going to get a good grade for it, and that's going to be that. So that's the plan. Of course, I have to add a statement of academic integrity. Please don't cheat. If you put the bare minimum in, you'll get the bare minimum out. I am expecting more than the bare minimum. It's tempting to allow yourself to be distracted during lecture, especially like during remote lectures. It's very easy to go pick up your phone. It's very easy if you've got a second monitor to kind of tab out and go do something on the other screen, or to go work on your assignments for a different class. And I'm just making a personal appeal to you right now. Don't do that, right? You get out of this class what you put in, pay attention, and I think that's going to be the best possible outcome, is on the other side of paying attention, locking in, and really giving it your best. I'm telling you to attend every lecture, but I'm not requiring you to attend every lecture. So I'm not going to take attendance. I just don't have the bandwidth or the mental energy to be like the attendance police or the cheat police. But this is what I'm asking you to do: is attend every lecture, ask questions, be engaged, work with others. And I think this could be some of the most fun that you've had at RPI. I certainly hope so. I do have a cold calling policy. So I reserve the right to cold call students and just say, hey, you, what do you think about this right now? I absolutely can't stand, this is one of my pet peeves, if I'm lecturing, and I get that, if we were all in person, I could kind of read whether or not you're understanding the material from your facial expressions and your body language. But I'm basically just, talking to my empty bedroom in my apartment right now. So it's a bit challenging for me as a speaker. And if we get to a point where I want to check in and make sure that everything makes sense, I reserve the right to just say a name and ask you what your opinion is on things. You don't have to be right, but I'm expecting you to say something. And I have this policy in place so that everybody knows, like, it is never safe to not pay attention. I want everybody to be paying attention. If we're in the middle of a really dense derivation on some orbit determination technique, and I go, and what would the measurement be? So and so, and you panic and you don't know the answer, that's totally fine. We're not going to shame anybody for not knowing the answer. If you don't get where we're going, that's probably my fault. But I want to know that, right? So I reserve the right to cold call. Give me an honest answer. Try your best. Don't be afraid of asking stupid questions or looking stupid. That's all. That's all part of the learning process. The other thing is, it might really be that you just can't answer the question, or you're having a bad day, or your pet died that morning and you really are just barely holding it together, or something like that. I've had days like that where I'm just, I'm in lecture but my brain isn't, right. If there's a real problem and I call on you, then our safety word is eject. If you say eject, no questions asked, I'm not going to follow up with you on that. It's like, good enough, that's fine. But I'm asking you not to abuse eject. Sorry, professor, I wasn't paying attention is a perfectly valid answer. But yeah, eject is there for if you're just having an abysmal day. So that's my cold calling policy. So the first homework assignment, which I will either post or email later today, is going to be a very easy 10% of your entire course grade. Basically, you're going to give me your resume. That's what it boils down to. So there is a fictitious company, which does not exist, that I've invented called the RPI Instrumentation Laboratory. And I'm going to post a job listing, and you're going to apply for that job. So part of this is you practicing applying for a job. So, when the time comes to apply for either internships or jobs, and I think most of you have kind of been down this road already. If you don't already have a resume, it is time to get a resume together. If you don't know how to write a cover letter, it is time to figure that out. And also, if you don't have a professional or at least a decent looking photo of yourself, it's a time to get one of those together as well. So your deliverables, which you'll be able to post this on LMS, will be a resume, a cover letter, and a headshot responding to this job posting that I send out. And so, yep, if you don't already have those things together, then now is really the time to figure it out. If you do have those things together, then you'll be able to, less than an hour of work, and boom, there's a whole letter grade in the course secured. So homework 0 is going to be due January 17th, so you've got some time to work on this. And right now, LMS is not cooperating with me, but when we get everything working properly, then you'll see a link that you can go and post your homework 0. So I call this homework 0 because it's not really a homework assignment. Like, you're going to get a letter grade for it, but homework 1 is when the math starts, right? So we'll get there later this month. Anyway, that is the end of my spiel. So I've been clocking it at a little over a half hour that we've been talking. So I want to do a 10-minute break. And if anybody has any questions or you want to talk about anything, then go for it. Anybody else, if you want to come back at, let's say, maybe 6:45 or a little bit thereafter, we can continue our discussion, and we're going to do a little math exercise. Let's see. Okay, yeah, I saw a message about course override. I can take a look at that. I'm going to be honest, I've not done that before. I don't know how to do that. But I do have SIS access as of a couple of days ago. So I should be able to give that the old college try. And we'll figure that out. We might need to figure that out together. If you want to stick around after class, which again, we're going to go through a math exercise and then we're done. So we'll be leaving early today. If you want to stick around, then we can talk about that. Yeah, we'll figure it out together.
Professor, quick question.
Yes.
One of my friends who's doing grad school right now was asking me about this course. Do you have like a PDF syllabus I could send them?
Oh, did I? Oh, I'm sorry. That's right. I sent out a PDF syllabus to everybody, but then I realized that you weren't on that email. Sorry.
That's
Yes,
all
I
right.
do. No, that's good. I'll send that to you. Actually, once I get LMS fully functional, once that's fully operational, then that'll also be there. Um,
Okay.
but yeah, if you want to send me, because I think the easiest way to do it is send me an email and just say, please respond to this email with the syllabus, and then I'll just respond to that with the syllabus. I think that's the way to do it.
Okay. Thank you.
Yep.
I have a quick question about the cover letter.
Yes.
I know most of the time those are like geared specifically towards the job. Do you
Yep.
want us to write it more in general or just like
Oh no,
gear it
I'm
in
going to
some
post a
way?
job listing. You haven't seen it yet.
Okay,
Yeah.
perfect.
Yeah. Sorry.
That
All
sounds
of this
good.
is if I could have had LMS fully operational before the class started, then you would already be able to go read it. Actually, just for kicks, do I have it? Hang on. Here's the syllabus. Um, we'll post this here. Stand by. I'm gonna post it here. I'll share this, but it is going to be posted. Uh, there we go. Share my screen. There we go. So this is going to be what the job listing looks like. So it's kind of similar to what you might read somewhere online. And yeah, so this gives you, it really actually is kind of a tongue-in-cheek just description of what the class is all about. But yeah, this will be what you're responding to. So you can tailor your cover letter to this.
Sounds good. Thank
Yep.
you.
That was a great question, by the way. Yeah.
This is almost. Wait, is my mic working?
Yep, coming through loud and clear.
This is almost entirely a joke, but do we get extra credit on the Kerbal Space Program thing if we do it in Realism Overhaul?
Whew. If you can do, uh, all right. I'm tempted to go, yeah, 10%, but then it's like, I gotta think through this. I'm gonna say no. But if by the virtue of you asking me that question, I can already tell that you've got the 5%. Like that, that's in the bag.
Yeah, I was planning
So
on doing an SSTO anyway.
yeah, you're good to go. Yeah, you're. I'm not worried about you. So yeah, but no is the proximal answer, but you're gonna be just fine.
That's what I figured. I just figured it would be a little bit funny to ask.
No, yeah, that's for sure. figure we'll start back up again in a second here. Let's see. Okay, so still sharing my screen. So I've got a kind of math mental exercise that we're going to go through for the next, I think it might be about 15, 20 minutes. We'll see how long it takes to get through it. And then we're all done for the day. And anybody that wants to chat about anything can stick around afterwards. So let me go ahead and resume the presentation. I've got a question for whoever feels like piping up, and not necessarily going to cold call anybody. We'll see how it goes. But yeah, just looking for someone brave to answer me. What is space?
I feel like the answer is like everywhere. Like all that we can see and visualize is space.
That's a solid answer. What I was looking for, and that's not a wrong answer. The answer I was looking for was, Professor, that's a dumb question. Because what is space, apart from, kind of a sense of panic and like, oh no, what's the right answer to this? It's like that's kind of an unanswerable question. Like, what does Paul mean by this? Can you be more specific, please? So what I want to walk through, this exercise is as much about solving the problem as it is about learning how to take a poorly constrained problem and turn it into something that we can actually solve with the skills and tools that we have, access to. So what is space? That's technically an unanswerable question, because it's like, is everything space? Is the Earth space? The Earth is in space. Is space where the Earth isn't? So let me rephrase this as a much more answerable question. At what altitude are we in space? I think some of you might actually know. There is a right answer to that question.
100 kilometers.
100 kilometers. Very good. That actually is the right answer. So that's the bottom line up front. Good job. We're going to talk about why it's 100 kilometers. But so the question, hopefully you can see that the question, at what altitude are we in space, is an infinitely more easy to solve question than just what is space. Like when am I in space? Okay, so now what we're going to say is, let there be some altitude, some number, some scalar value, some h for height off the ground, where if you were above that altitude, you are in space, and if you were below that altitude, you are somewhere in the atmosphere. Right? And there is an actual right answer. That's 100 kilometers. So we're going to talk about why that's the case. And also, I'm going to get a little bit of practice. So I've got a kind of pen tablet here, and I'm going to go through and handwriting has gotten a little bit rusty here. So here's the problem as I understand it. So you've got the Earth. Here's the Earth. It's a sweet Earth, you might say. And let's say this Earth has some radius, which we're going to call r(e). And then let's say that there's an atmosphere around the Earth. And there's some height to that atmosphere, h. And then outside is space. And then this is Earth. There we go. So there was a scientist, engineer, who first tried to solve this problem. So you might think that where is space falls under the realm of astronomy, but it really doesn't, actually. Surprisingly enough, astronomy deals more with questions about things that are insanely far away. The first group of people to really care about what is space and what isn't space was actually the aerospace community. It was us, because we wanted to be able to say, has this particular vehicle been to space or not? Right. So it's actually surprisingly recently in history that we started really thinking about where space starts and where the Earth ends. You might say that space is where the atmosphere stops. But those of you that are familiar with the way the atmosphere works, it doesn't really stop. It kind of, peters out. Like it gets thinner and thinner and thinner. But there's never no atmosphere. I mean, even space isn't a perfect vacuum. There's still stuff. It's just very, very little stuff. But for example, the International Space Station, which is in low Earth orbit, actually needs to account for drag, right? It's got these massive solar panels and thermal radiators that act essentially as sails or as drag nets that slow the whole thing down. And we need to perform maneuvers every once in a while to boost the orbit of the space station. So there is an appreciable amount of atmosphere, not enough for the whole ISS to come crashing down in a few hours, but enough that if we did nothing, its orbit would decay over time appreciably. So you can't just say that space starts where the atmosphere stops. It's not that simple. So I'm going to introduce someone named Theodore von Karman. Some of you already know the punchline to this. So Theodore von Karman. Really, there should be little accents over the A's. He lived from 1881 to 1963. And he was an academic. He actually, I just want to mention this really quick. He had a graduate student named Richard Gilman Folsom. Who can tell me why that name sounds familiar?
The library's named after him.
Yep. Richard Gilman Folsom was a former RPI president, and we have a library named after him. So Richard Gilman Folsom's PhD advisor was Theodore von Karman. So small world. So just for the sake of having this in the notes, this guy was an RPI president. So small world. So what we're looking for is the edge of space. So we seek the line where aeronautics stops. And astronautics starts. So you could think of this as where inertia triumphs over lift. Okay. So where does space start? Well, how about it's where wings are useless? That's the very simple high-level definition that Theodore von Karman came up with. So von Karman wanted to say, at what altitude are your wings not doing you any good anymore? You're just in space, right? So imagine you've got a space plane, something like the X-15, that would fly higher and higher and faster. Past a certain point, it's not really flying, it's floating, right? So let's try to find where that is. So now, what we're really saying is, at what H is a vehicle in space. Okay. So what we need, this is a more formal definition, is we are looking for the altitude at which an aircraft would need to travel poor handwriting, would need to travel so fast to maintain level flight that it may as well be in orbit. So hopefully this makes some intuitive sense. So if you've got a aircraft We know that if you want to fly higher, you've got to fly faster. And you can imagine that if you fly even higher, you would fly even faster, and so on and so on and so forth. But there's going to be a limit, right? Because at some point, you're going so fast that you're just at your orbital velocity. And at that speed, your wings are really doing nothing for you. You're just orbiting the Earth, right? To quote from Toy Story, you're not really flying anymore, you're falling with style, right? So what we're going to do is we're going to actually derive that velocity. That's going to be kind of our introductory exercise here. So this math exercise is really going to be at a high school math level. So my apologies. If you're looking for more rigor or more of the fancy linear algebra, you won't find it here. You will definitely get that later in this class. But for now, this is going to be almost hilariously simple. But just to get everybody warmed up and talking about space. So let's talk about orbital velocity really quickly here. Orbital velocity. So imagine that you've got just some cube floating through space. It's got some velocity v. And let's say that as it hurls through space, it's going so fast that it's got some centrifugal force acting on it. We're going to call that Fc. So as it's hurtling around the Earth, it's basically has a tendency to want to be flung out by its own momentum. We're going to model that as centrifugal force. But then also, it's got gravity acting on it. And something that is in orbit is in a state of perfect balance between centrifugal force and gravity. And so we're going to say, in the case of something that's in orbit, that Fc is equal to Fg. So some of you might be familiar with this. What is the high school physics equation for centrifugal force, or for you've got something that's traveling, circular motion, and there's a certain amount of force that's required to keep it on that circular track. Does anybody remember what that equation is? Or want to take a crack at it?
I'm going with mv squared over r.
Very good. Yep. mv squared over r, where m is the mass of the object in question, v is its velocity, and r is its radius. Okay, so in this case, radius would be not the altitude. It would be more like the distance from the center of the Earth to the spacecraft. So we're going to say that r is the radius of the Earth plus your altitude. Okay, great. Now this is equal to Fg. So from somebody else, what is the force of gravity according to Newton's law? Anybody remember Newton's law of gravitation?
G big M small m over r. If I remember correctly.
Perfect.
Over r squared.
Very good. You got it. G, so the gravitational constant. Big M, so the mass of the more massive body, that would be the Earth in this case. Little m, the mass of the vehicle, so there's an m on both sides. And then this is over r squared. Great. Now, just to simplify things, I'm going to define a new parameter, which is the Earth's gravitational parameter, which is the Greek letter mu. And I'm going to put the triangle equal sign, which means is defined as. So this is a new parameter that I'm saying, let there be some mu, which is equal to gm. So you think about it, this is unique to the Earth, but the mass of the Earth times the universal gravitational constant is this term mu. It's just going to mean that we have to do a little bit less writing as we go through with our math. So if we go through, we cancel, we replace, what you end up with is that v squared is equal to mu over r, or orbital velocity, and this is for a this is for a circular orbit, is just the square root of mu over r. Okay, great. So those of you that have taken spaceflight mechanics, you've seen this equation derived. There's much more rigorous ways to arrive at this solution. And of course, something that is on an elliptical orbit, its velocity is constantly changing with respect to time. So this is a gross simplification, but it's good enough for now. Now, what about something that is said to be in a state of spaceflight? So something that's actually flying or orbiting. So now we're going to draw a slightly more complicated free body diagram. Here's my best rendition of, I'm going to kind of scroll down a little bit, my best rendition of an X-15. So wish me luck. It's got like a little cab thing, and then it's more narrow. It's got a big vertical stabilizer, and then the body goes like this, and then it's got this little stumpy wing, and it also has like that, and then maybe it's got another wing. And then the vertical stabilizer says NASA. And then there's the cockpit. Someone's having a good time. Okay, so now you're on an aircraft with some forward velocity v. And in this case, once again, you've got gravity acting on the vehicle. You've also got centrifugal force acting on the vehicle, same as before, but we've got lift. So kind of a script L. So what is the equation for lift in this case? My aero people, remember the simple kind of freshman level aero lift equation? As I'm looking, I actually just found a typo in my notes. Remember, like 1/2 rho something something. Somebody help me out.
Is it 1/2 rho v squared times the platform area?
You're basically there. So we're at, and thank you, by the way. I'm always like kind of awkward when it's like, somebody say something, please. So we've got mv squared over r is our centrifugal force. So that's the natural tendency of the vehicle to fly off because of its orbital speed or its near orbital speed. Plus lift is going to be 1/2 density, coefficient of lift, projected frontal area, velocity squared. So that's what you were getting at. And then this is equal to, we're going to write this as mu m over r squared. Okay, great. So, let's think about this for a second. Velocity, well, ultimately what we want is some equation for velocity. Projected frontal area is something that you can look up, right? Like for a specific vehicle, we can look that up. Similarly, coefficient of lift, you can go and look up. What about density? Isn't density of the medium that you're traveling in, like the air, also a function of altitude? So that kind of makes this a little bit trickier, right? So I'm going to borrow from those of you that have taken spaceflight mechanics and used the Howard Curtis textbook. There's a really simple inverse exponential atmospheric density model. So this is Howard Curtis textbook, example 11.3 has this equation. So I'm borrowing it. Rho is equal to rho naught times the exponential function of negative h over h naught. That's e to the power of negative h over h naught. I just like to write it this way. Okay. Where rho naught is 1.225 kilograms per meter cubed. That's the sea level altitude, right? And then h naught is some reference altitude, which we're going to say is 7.5 kilometers. And we need to be careful of our units. If we're going to do all of our work in kilograms and kilometers, which I think kilometers makes the most sense, then this is actually 1.225 times 10 to the 9th kilograms per kilometer cubed. Okay, great. So now density is itself a function of a constant, another constant, and an exponential of our altitude h. So what we really want is velocity as a function of h. That's kind of what we're after here, right? So let's go through and fill in some things. Now, first of all, r, I don't know who r is. I want h. So we're going to replace r with the radius of the Earth plus h. And then we've already kind of supplanted gm with mu. So my new equation is going to look like this. M v squared, the Earth, plus my altitude, plus 1/2 rho naught exponential function of negative h over h naught. Coefficient of lift, projected frontal area, velocity squared is equal to mu m over radius of the Earth plus altitude squared. Okay, great. Now, solve for h. Oh, I'm sorry. Solve for v in terms of h. So relatively simple algebraic manipulation. I'm just kidding. It's impossible. There's no way you're not going to solve for v in terms of h. It's going to be an absolute nightmare. So what I would do, what I recommend, is solve for v in terms of h numerically. And plot. So what do I mean by that? So we can find the space flight velocity by plugging in. So you would need the mass of a particular vehicle and the projected frontal area of a particular vehicle and the coefficient of lift of a particular vehicle. And then rho naught is known, h naught is known, radius of the Earth is known, Earth's gravitational parameter is known. And so what you would do is numerically say, at this altitude, my space flight velocity is this. At this altitude, my space flight velocity is this. Now, this equation is not taking into account things like drag. We're going to ignore that for now. We're just going to say, let's solve this equation numerically for velocity as a function of altitude. And then you can co-plot that with your good old-fashioned orbital velocity. And so this is like one of those cooking shows where it's like, oh, actually, I put something in the oven before we started filming. And if you're following, then hopefully this next makes sense. So I already did this. So I use numbers from the X-15 spaceplane. If you're familiar, a lot of really cool history with the X-15 program in the 1960s. Neil Armstrong was an X-15 pilot. So I use this mass, this projected frontal area, and this coefficient of lift. And I use the Howard Curtis atmospheric density model. And I just plotted the velocity of spaceflight along with the velocity of orbit. And they converge, and they basically become the same line. And this is where it's in the eye of the beholder. You could argue that they converge at 80 kilometers. You could argue that they converge at 120 kilometers. It just so happens that 100 is a nice round number. And that is good enough for me, at least. Hopefully it's good enough for you. So from this, Theodore von Karman said, let it be the case that 100 kilometers is the edge of space. And we've been running with that ever since. So those of you that have heard of the Karman line or the von Karman line, that's what that is. If you're above 100 kilometers, you are in space. If you are below, you are not in space. And this is why. Now, before Theodore von Karman came to this conclusion, I believe it was before, the United States Air Force said, 50 miles is probably about right. And that number also stuck. So there's a number of people that have been above 50 miles, but below 100 kilometers that the Air Force, and I believe that just generally the US military recognizes as being in space, but then people like NASA will go, oh, that's not space. So there's still some debate about where exactly the edge of space is, but most folks adhere to the von Karman line. So hopefully that makes sense. Hopefully you're able to follow the logic and the reasoning there. And I want to thank everybody for their cooperation. Any questions on this, or are we good to wrap up for today?
I asked a question earlier
Oh,
in
what was
chat. Just since it's kind of off topic from this, but since you've taken a good amount of graduate courses at RPI, which ones would you say were the most impactful for your career?
Oh, that's a great question, actually. Yeah, definitely. I would say, I mean, the class that I took, which is the equivalent of this class, which was spacecraft navigation from Dr. John Christian, I use something from that class almost every single day. And that is basically this class. Like, this is the spiritual successor to that class. So that's a little bit of a shameless self-plug, but that's because I actually took a navigation course and then went into the field of navigation. Apart from this class, I would highly recommend anything that is space related if you want to go work at NASA or somewhere that is NASA adjacent, like Lockheed or Boeing or some of the smaller companies. anything space related. I know there's a kind of a growing space cohort at RPI, so I would recommend taking all of those. I got a lot out of Dr. Jason Hickens' numerical design optimization class, and we'll be actually using some of the techniques from that class in this class. I'll re-present them to you, so you're not expected to have taken that. But design optimization is phenomenal. Systems analysis techniques, pretty much anything that Dr. Mishra thinks is a good idea to teach is a good idea for you to take if you want to go into anything that looks like this. And also optimal control theory, nonlinear control theory. I got a lot out of those as well. You can easily go down a rabbit hole and spend a lot of time on controls, which I did. I spent a good time on that. And then also robotics. I know Dr. John Wen used to teach robotics, and I think he still does, or one of his former students does. But robotics is kind of the next door neighbor to guidance, navigation, and control. There's a lot of overlap between the two communities. And so I recommend this class for anybody that wants to go be a roboticist, and I recommend robotics for anybody that wants to be a navigator. I think they're both a good idea. But those are some of my favorite classes, and I guess this is being recorded, so I hope that anybody who's listening to this who does not hear their course listed does not take it as me bad-mouthing it. Those are just the ones that popped up into my head first.
Thank you.
Yeah, absolutely. So with everyone's permission, I'm going to stop the recording, but I'm going to stick around. And so with that, class is dismissed. Thank everybody for lecture from the spring 2025 Intro to Spacecraft Navigation. So thank you, and class is dismissed. But of course, I'm going to stick around, and I'll see you all on Thursday if you want to take off now.